One thing you have to be able to do is look at data and pick out relationships. It's not enough now to say that things increase. You need to talk about how they increase and the mathematical relationship there. Let's have a look at this table for stopping distances. It's typical of what you might expect in your Additional 3 exam. We can see that the speed increases down the table. We can see that the thinking distance and braking distance, and therefore the stopping distances, all increase too. But what are the relationships there? Well, the thinking distance, if the speed increases by 20, 40, 60, 80, 100, that increases by 4 metres each time. There's a linear relationship. We can also say that it's proportional, because if I double the speed from 20 to 40, I double the thinking distance. If I double the speed from 40 to 80, I double the thinking distance. Let's have a look at the braking distance and see what relationships we can see there. Again, it increases. But if I double the speed from 20 to 40, what happens to the relationship between the braking distance? What factor does it go up by? Well, 2.5 is a quarter of 10, so you have to multiply 2.5 by 4 to get 10. It quadruples. If I double the speed, the braking distance quadruples. Let's see if that's the same for 40 to 80. If I double the speed from 40 to 80, then again I multiply the braking distance by 4. I get a greater increase. You need to remember that. If I double the speed, I quadruple the braking distance. It's a squared relationship. In this exam question from January 2012, they ask you to plot the graph for the braking distance. Let's have a look what it would be like. The first one is 2.5, then 10, then 22.5, then 40, then 62.5. It's a curve. Let me try and draw the line of best fit. Hopefully, when you do this in an exam, you'll get a better curve than me, because I'm drawing on an iPad screen with my finger. Looking at this graph, you can see that the faster you go, the bigger the influence braking distance has over the stopping distance. That's due to this quadruple relationship. Doubling the speed quadruples the braking distance. The last thing to be aware of is they might trick you and not double the speed. They might triple the speed. If you go from 20 to 60, what factor is braking distance multiplied by now? Let's have a look. 20 times 3 is 60. What relationship is there between 2.5 and 22.5? Well, I'll divide 22.5 by 2.5 and see how many times we need to multiply upwards. You'll find that it's times 9. So if we multiply the speed by 3, the braking distance is multiplied by 9. What's the relationship between these two numbers? Well, 3 squared equals 9 in the same way that 2 squared equals 4. It's this square factor that makes this curved line here. You need to be aware of whatever the speed is multiplied by, the braking distance is multiplied by that factor squared. So the speed is multiplied by 4, the braking distance is multiplied by 16, 4 squared, and so on. This is why braking distance is always a bigger influence on the stopping distance than the thinking distance will be. Where does this squared relationship come from? What's the science? Well, we need to go back to our formula for kinetic energy. When we're stopping a car, we need to dissipate, we need to get rid of all of the kinetic energy, all the movement energy of the car. But if our car is going twice as fast, it has twice the speed, it has 4 times the kinetic energy. That squared factor I was talking about in the previous slide is due to this squared here. Doubling the speed quadruples the kinetic energy. Trebling the speed multiplies the kinetic energy by 3 squared, 9, and so on and so on. Because we have more and more kinetic energy, it takes longer and longer distance to dissipate that kinetic energy, and therefore the car needs longer to stop. I hope you found some of this discussion useful, and you remember to look at data if you're asked to describe trends. To say something's increased is not enough. We always need to include the factors. Good luck.